Now, let's scratch our heads a little bit today and look at 1997 question 9 part B. This came clearly out of an evil set of pints between applied maths teacher and a physics teacher. If we look at it, it does look like a bit of a mess. So let's just kind of pause. We have a balanced B hanging a weight in a beaker, with the mass of the beaker, over another scales. Okay, so first things first, if we have a weighing scales, it will measure the weight. Okay, so weight equals mg. It will confuse you and pretty much every other junior science student by displaying the mass. So 2.5 kilograms is a mass. So scale says 2.5. What it means the force, because that's what weighing scales measure, they measure force or balances or any of those things, is 2.5 G. All right, so now we got that one out of the way, because otherwise it's all going to go horribly wrong. All we need to do is break this up a little bit, okay? And there's a couple of ways we can do it. So for the moment, I'm going to take the block in the water. All right, this is the block. And we just look at it on its own. It is a force downwards. What's its mass? We are not told. So we're going to call its weight G. Okay, or W. Okay, wait a minute. We'll worry about it. We can break that out into mg's and stuff later on if needs be. And we have an upwards force on it. All right, which is the buoyancy. We also have an upwards force on it, which is the tension in the string. All right, so in this case, the weight equals the buoyancy plus the tension. Now, look at the scales. This is B. And it has the same tension going down and it reads 2.5. So we know that T is 2.5 G. Okay, because the only force going down, the scales reach 2.5, so 2.5 G. Now, let's just tidy this all up a little bit. What we then know is, therefore, the weight is the buoyancy plus 2.5 G. Okay, different ways to go at it, but that's one of our initial equations. The second thing we're going to look at is the other bits of it. Okay, you could actually look at the system in its entirety if you like, but this is the beaker. I'll call it beaker. Yeah, the beaker plus the liquid. Beaker plus the liquid. So there we are. I'm actually going to draw this as sort of a proper beaker, just to remind myself, because unusually this has a mass. And there is our liquid. Now, in our liquid, there's a gap. And this is where this equation, this gets a bit tricky. So this is my beaker. This liquid is liquid. No, we're not told if it's water, so we're just going to call it liquid. Actually, in part 2, we didn't define its relative density. What this here is a gap left by the block. Okay, the block isn't here. This is only the beaker and the liquid. All right. Because the liquid is exerting a buoyancy force on the block, the block is exerting the same buoyancy force on the liquid. All right, and this is one that kind of keys to this whole question. All right. We also have the mass of the beaker, so that's 1g, and we have the mass of the liquid, which is 1.5 g. All of those guys are sitting on the scales, which I can't really draw here, but if you think of the forces down, we have 1g plus the buoyancy plus 1.5 g. All of that sits on the scales, which reads 7.5, so we know that that means the force on the scales is 7.5 g. Quick bit of tidying up, we see the buoyancy is 5 g. All right. Now, let's just double check in our question what exactly we're looking for. We look for the mass of the block. So let's rewind a bit here. We'll go to the weight of the block and we can take it from there. So if we come up to the top of the page here, there's a bit of space. We know the weight of the block is the buoyancy plus T is the buoyancy plus 2.5 G. So the weight of the block equals 5G plus 2.5 G. So the weight is 7.5 G. Be careful, because like I said, it was an evil gathering of physics teachers and applied maths teachers. They wanted the mass of the block, so they're looking to trip you up in this little one here. In this case, therefore the mass is 7.5 kilograms. All right. So actual maths in this one isn't tricky, but the figuring out what's going on, what's being asked, is quite tricky in it. So part 2, relative density of the liquid, SL. What do we know? What do we know? Well, if we look at the relative density of liquid, we'll probably have a crack at this through buoyancy. Okay, so if we think of our buoyancy equation, buoyancy is the relative density of the liquid by the weight of the object over the density of the object. Let's see if that is going to get us there at all. And no, because if we look back through the question here, we don't really have the density of the object. So scrap that one there for the moment. The other way to go at this one is to find out the density of it. So let's see if we find out the density of the gap here. Well, actually, we'll just find the density of the object. That's not too big a deal. We know its weight equals V rho G. And the key little bit in the question that's giving me a hint to go this direction is we know the volume equals 0.01. Okay, that's a nice little clue. So the weight here is 0.01 by rho by G. The weight is, of course, 7.5 G. Cancelling my G's. Density equals 750. Okay, now, at this point, little alarm bells might be going off in your head, because that is rather low for a block that's not floating in the water. Okay, in this case, the specific density of the object is going to be 0.75, so just 750 divided by 1000. That seems odd, but we're looking for the density of the liquid, so I'm going to expect the density of the liquid to be less than this again. All right, well, let's come up to here. So the buoyancy, which is 5G, so using buoyancy equals SL W over SO, because I have pretty much everything here except SL, so that is 5G equals specific density of the liquid we're looking for by the weight. If we go back here, 7.5 G, lovely, my G is going to cancel, all over 0.75. Look at this, they're getting nice now, they had to be nice to us eventually. So let's cancel out our G's, straighten up the page there, they're going to go. So we know that 5 equals, and actually if you realize if we tidy this all up a bit, that's just 10 SL. Stick in a calculator if you're unsure about it, but again 7.5 is just 10 times 0.075, so the specific density of the liquid is 0.5, which is just what I would have expected given the unusually low specific density of the object. And there we have it.